In today's lecture, we will talk about bridge sampling method for estimating the marginal likelihood, and then we'll apply the technique to our real data set, and then we'll move to, if time permits, then we'll move to a new chapter. Now that new chapter is on linear regression. My plan is to create that chapter in the HTML format. I did not get time to do that. So initially I have posted the PDF version, but I will eventually convert it into an HTML file. And why we talk about bridge sampling estimation? There are different ways of estimating the marginal likelihood. And as we have seen, estimation of the marginal likelihood, the key component for calculating Bayes factor or for finding evidence for a proposed model, is very difficult when you have multiple parameters. And there are different methods. We talked about one, which is harmonic mean regression, harmonic mean method. And the very first one, which is simple Monte Carlo integration of the likelihood function. When you sample your parameters from the prior distribution, is very inefficient. Then we have little bit of modification, which is harmonic mean method. And then people have also talked about important sampling estimation of the marginal likelihood that did not resolve all the issues. Therefore, we have this bridge sampling technique. Now, bridge sampling technique is still a very general technique and seems to perform well, but there are rooms to improve the bridge sampling technique as well. And what is the key result of the bridge sampling technique is that for the application of the bridge sampling, we need two things. One is the proposal distribution, and the other one is the bridge function. So if we choose them properly, these two things, then we will have a better estimator. Better estimator in the sense of lower variance. And what we have seen is that the optimal bridge function is H star, which is a constant C times. That constant does not matter. Why? Because if I plug in this H star right here in the numerator and in the denominator, that C will be cancelled. Therefore, we do not need to pay attention to the constant term. But what matters is the part involving theta. And this has this structure, S1 times P data given theta. P data given theta is our likelihood part. Pi theta is the prior part. S2 is another constant. P data is the marginal likelihood times G theta. G theta is the proposal distribution. Now, what are the choices of S1 and S2? Optimal choice for S1 is this guy, M of nu over M of d nu. So look at this. For the bridge sampling estimation of this marginal likelihood P data, we are doing two samplings. One sample is from the proposal distribution. Okay, so here the numerator is calculated based on the Monte Carlo sample from the proposal distribution G, and the denominator is based on another sample from the posterior distribution. So A1, A2, A, M nu is coming from G, and B1, B2, B M denominator is coming from the posterior distribution. And the number of samples that we are taking are M sub nu and M sub d nu. If you take equal number of observations, then S1 and S2 will be 1/2. Otherwise, it will be the proportion. Very important thing is that this optimal value H star depends on the quantity we want to estimate marginal likelihood. Therefore, it is done iteratively. You cannot calculate in one single shot. You have to do it multiple times. Second thing is this G theta, the proposal distribution. Proposal distribution should be, if it is to different from the posterior distribution, that will give you inefficient estimation, inefficient estimator. Therefore, we try to choose proposal distribution somewhat close to the posterior distribution. The software uses normal proposal distribution. So that means what? It calculates the posterior mean and posterior standard deviation of each of the parameter, and then assume that the proposal distribution has the same mean as the posterior mean and the same standard deviation as the posterior standard deviation. And this is the interesting paper. The reference paper for this technique is given here, 1996, simulating ratios of normalizing constants via a simple identity. So in the Bayesian paradigm, if you want to do testing of hypothesis or want to get evidence, real evidence for your model, you must have the marginal likelihood. Now, you may say Bayes factor is an approximation of the marginal likelihood. Yes, it is true, but it is not a very good approximation. Now let us look at how do you calculate it. This is the theory part, not the theory. Actually, I have not proved anything. Theory means you prove result, right? Here I just talked about how it was formulated. What is the reason behind taking this form? Now we talk about estimation. Remember, our problem is that we have data from 4 groups, and we wanted to check if the underlying group means are the same or different. So we have 2 competing models. One model where we assume underlying means are the same, and the competing model is where we do not put any restriction on the underlying means. So this is the summary of the data. Summary means Y bar, you have number of observations from every group, then SI, sample standard deviation, then you create this my data. It should be a list. And these are the prior parameters, mu 0, gamma 0 square. Gamma 0 square is the prior variance. Okay, so I have corrected it, prior variance up there, but I forgot to correct it here. And nu 0 is the parameter for sigma square. Sigma 0 is again parameter for sigma square, eta 0, and tau 0 too. For the calculation of the marginal likelihood through bridge sampling method, you need to provide the log of the posterior function. So log of posterior is calculated as follows. First, look at this. Log posterior means minus n over 2 log of sigma 2. Then your sample size minus 1 times sample variance. And then sample size times y bar minus theta 1, right? Theta 1 means the parameter, mean parameter, square of it and sigma square. So this is the data likelihood part, and the following parts are the prior distribution part. Prior distribution, and this is the log posterior calculation under the null hypothesis. Therefore, I put this 0 to signify under the null hypothesis. Then, so this is needed. Another thing is, previously we did the MCMC sampling. So we already had this theta value stored in H0 stored theta. Mu was stored here, sigma squared stored here, and tau squared stored here. You need to have an MCMC object before you invoke that function, bridge sampling function. Okay, and then this library, this bridge sampling technique. And so this is bridge result, bridge sampler. You have to provide samples, which is the MCMC object. So after you do the posterior sampling, you need to present it in a nice form, and this is called MCMC object, and this object can be done in the CODA package, CODA package. Second thing, log posterior. You have to provide the log of posterior density, then data, and then lower bound and the upper bound of the parameters. Sometimes you do not need to provide lower bound and the upper bound. But when I tried to calculate it for our data example, it did not work. It was giving me error message every time. Then I asked ChatGPT to solve this issue. ChatGPT told me, put this lower bound and upper bound. It worked. It worked. And the method, look at the method part. So it says, how do you want to do the proposal construction? It's a normal proposal construction. So you can play around with this. This is a wonderful function. You don't have to write all the optimal function and other things. It is done in the package. The results, you see results, iteration 1, 2, 3, 4. Because the optimal H was calculated iteratively. And it returns log of marginal likelihood is minus 55.47. Log of marginal likelihood. Then I attempted to calculate this marginal likelihood under the alternative hypothesis. Therefore, I call it log posterior of 1. 1 means alternative, I just want to say. At this time, I have 4 parameters, theta 1, theta 2, theta 3, theta 4. Okay, so this is how I do it. And then log posterior. You see, this part remains the same as before. What is changed is the log likelihood part, log of the data likelihood given the parameter. Then MCMC samples, again, I repeat the same thing. Lower bound, upper bound, and then this bridge sampling, bridge sampler. And you get minus 50.03 as the log of marginal likelihood. So which marginal likelihood is larger? Tell me. Previously, it was minus 55. This time it is minus 50. And you do e to the power, right? So it is about e to the power 5. So marginal likelihood. So if I calculate marginal likelihood of the null, over the alternative, then it is e to the power minus 5. E to the power minus 5 is very small, right? Very small. That means you have very strong evidence in favor of the alternative hypothesis as opposed to the null hypothesis. As opposed to the null hypothesis, you have very strong evidence for the alternative. That means these data provide evidence that the underlying means are different. And also, this is the first time I'm using this bridge sampling function to calculate the marginal likelihood. So please make a good use of this function to your problem. It's a very general function. As long as you can write down the log likelihood, log posterior, then you can use this function easily. Obviously, you need a lot of thoughts if you want to apply in a very non-parametric setting where you have very complex prior distribution. I don't know. I cannot think of any easy way to do it. But for your problems, most of your problems are very parametric problems. And there you can easily write your, obtain your bridge sampling estimator of the marginal likelihood. One important assumption we used in all this analysis is that the population variance is the same across the group. This is called the homogeneous variance assumption. We assume that underlying population variance is the same. They are not changing over groups, but that may not hold in many cases. And this is the scenario of unequal variances. And I think I should first talk about, before the unequal variance, the classical technique of testing the hypothesis. So the classical technique of testing this hypothesis is that you have y11, y1n1, and the corresponding mean is y bar 1, corresponding sample variance is S1 squared. And you have several such groups, right? 4 groups. So Y41, and S4 squared. The underlying means are mu1, mu2, mu4, and underlying population variances are sigma squared, and they are the same. This is our setup. This has been our setup. And the classical technique of testing this hypothesis. Versus the alternative is at least one of the means is different from the rest. And we do, the technique is known as analysis of variance. Analysis of variance. ANOVA. So it is at least recorded. You can watch it later. If I get time, then I'll write it. Not now. I mean, towards the end of the semester, I'll write it in my class note. Did not get time to write it now. So ANOVA is a very easy technique, very easy technique. You just need a table, ANOVA table. And it has several columns. Column 1 is called source of variation. And the SV stands for source of variation. And then sum of square, then degrees of freedom, then mean square, then F statistics, and then p value. How many columns? 1, 2, 3, 4, 5, 6. 6 columns. Source of variation has, okay, and how many rows? So this table has 6 columns, and it will have 2 rows within the table and 1 row outside the table. So 2 rows, 2 plus 1, 3. Source of variation, it is between, and this is called within, and this is called total. Sum of square has the following formula: n sub I y bar I minus y bar square over I equal to, now in your case it is 4 groups, therefore you sum over I is equal to 1 to 4. But if you have many groups, you just sum over those groups. Within has the following formula: I is equal to 1 to 4, j is equal to 1 to ni, yij minus y bar I square. I'll come to this part later. Next, move to degrees of freedom column. Degrees of freedom, first is the total degrees of freedom. It is the total number of observations minus 1. So it is n minus 1. N is, in your case, n1 plus n2 plus n3 plus n4. And degrees of freedom for between. Between means between treatment, degrees of freedom. How many treatments we have? How many groups we have in the data? 4 groups. So it will be 4 minus 1. So 4 minus 1. Whatever number of groups you have, you just subtract 1 from it. And the total is n minus 1. And you subtract 4 minus 1 from n minus 1. That is your within degrees of freedom. Okay. This is very easy. You see, the bottom row always gives you the total. So if you know the bottom row and one of the 2 rows within the table, then you can figure out the other row of the table. Just subtract. Mean square. Mean square is sum of square divided by f. Sum of square divided by df. Sorry. And f. So this one is called mean square between, and this is called mean square error. And this is mean square between divided by mean square error. and this is the p-value, and this p-value is calculated. How it is calculated? It is the probability that the f random variable with degrees of freedom. So these degrees of freedom is called df1, and this is df2. So this is df1 comma df2 greater than this guy, whatever you calculate. That is your p-value. Once you have the p-value, then if p-value is very small, you reject the null hypothesis. If it is not that small, you fail to reject the null hypothesis. This is that simple. So let us now figure out what is this guy. This guy this is in I minus 1 sample variance. Ni minus 1 sample variance. In our data, we have that sample variance part. We have Ni, so we can easily calculate this part. And what about this y bar I? Y bar I is the group sample average. It is given. What about y bar? Y bar is the grand mean. And that grand mean means it is y bar 1. I'll show you grand means, how to calculate the grand means. Y bar is in 1 times y bar 1 dot 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 in 4 times y bar 4 divided by in, that is the grand mean. Not y bar 1 plus y bar 2 plus y bar 3 plus y bar 4 over 4. The reason is the sample sizes are varying. Therefore, you need to take into account that sample size aspect. So let us do that in R. And since this is a classical method, there is no use of the following part. Simply the data part is needed. The grand mean, okay, y bar, calculate y bar, which is Ni times y bar I, sum divided by sum of Ni. This is y bar. So now we calculate SSB. What is SSB? SSB is this guy, sum of square between. Okay, this is known as SSB. And this guy, the this guy is SSE, sum of square error. So SSB is y bar I minus y bar square times Ni Okay, now SSE. SSE is Ni minus 1 times SI square and sum. Degrees of freedom, df1 is 4 minus 1, df2 is n minus 4. N, what is n? N is sum of ni minus 4. MSB equal to SSB divided by df1, and MSE is SSE divided by df2. And F statistics is MSB divided by MSE. So let us do this. So it is 6.81. Now let us calculate the p-value. So p-value is 1 minus, so p-value is the probability that the f random variable greater than this f statistics value. And in R, generally, you get the lower tail area, not the upper tail area. But the p-value is the upper tail area. So what I'll do, I calculate the lower tail area, subtract it from 1. So 1 minus PF, this is the PF stands for the cumulative probability of the F distribution. F stat df1 df2. So so this is our p-value. So p-value is 0.0040. So typically we test the hypothesis at 5% level. And since the p-value is smaller than 0.05, we write our conclusion that we reject the null hypothesis and conclude that the data provides sufficient evidence in favor of the alternative hypothesis. 0.05 is one level. Another typical level is 0.01 also. 0.01, if you even test at 0.01 level, you still reject the null hypothesis. P-value is smaller than 0.01. Now, the meaning of this level of significance. When the level of significance is 0.05, what is the meaning? It means the probability of type 1 error of this procedure is 5%. Okay, so that means when the null hypothesis holds, 5% of the time you reject the null hypothesis. So this is the probability of type 1 error. Think about what is happening. This is the probability of making a wrong decision, right? Null hypothesis holds truly. That means you desire not to reject the null hypothesis, but you are rejecting it. What is the probability? The probability is 5% if you test at the 5% level of significance. So 5% of the time. So if you repeat this procedure, you sample from the population, calculate the test statistics, and decide whether you reject or fail to reject based on that 0.05 cutoff. It means your test has 5% probability of rejecting the null when the null holds truly. And so you see, to interpret this probability, you need to think about the hypothetical scenario that you sample many times from the underlying population. But for your case, you just have a single data set. For your single data set, you do not know what is happening. Okay, what is happening. But the procedure, so this is one of the issues of the classical method. Classical method guarantees about the procedure, but it does not tell you what happens for your real data set. Your real data set could be one of the cases. On the other hand, the Bayesian method does not rely on what is happening in the hypothetical scenario, hypothetical setup, but it tries to calculate things. Things means the credible interval and other things in the context of the current data set. Therefore, Bayesian method also does not calculate the p-value. Bayesian method does not calculate p-value. It calculates only the evidence for different models and checks the evidence, but it does not associate any type 1 error probability or type 2 error probability. But definitely, the classical method is very easy, very fast. Here I did the coding because I did not have access to the original data. If I had the individual level data, then I could have used simply one way function or ANOVA function of R that does calculate everything for me. It calculates all the sum of squares, all the statistics p-value, if I had the access of the raw data. Since I have the summary level data, I had to calculate all those quantities through the formula. But even then, it is very simple, as you see. As you see here, and p-value, that's it. So the good news is Bayesian method and the classical method both are giving the same conclusion, right? Although it is not guaranteed, but here we reach the same conclusion. Bayesian method favors the alternative hypothesis very much. Here we also reject the null hypothesis. That means we are favoring the alternative hypothesis. One thing I want to warn you that for the classical method, if your p-value is large, you never say, I accept the null hypothesis. You only say that we do not have enough evidence against the null hypothesis. In the classical method, it's not about accepting the null hypothesis. It's all about the alternative hypothesis, whether we have enough information in favor of the alternative hypothesis. And that is also different from the Bayesian analysis. In the Bayesian analysis, whatever has the higher marginal likelihood, we accept that model. We accept that model. All right. So here again, in the ANOVA, we assume the variances are the same. Variances are the same. And ANOVA is also quite robust in the sense, even the variances are not the same. If they vary a little bit, the performance of the F statistics is very good. It maintains its nominal type 1 error rate and performs very good. One way to check the variance assumption is you check the minimum sample variance of the 4 groups and the maximum sample variance of the 4 groups, and check if the maximum sample variance to minimum sample variance is more than 4. If it is more than 4, then you should be concerned. But if it is not, then it is all right to apply the standard technique where you assume underlying variances are the same. In this example, the maximum is 9.3, sample variance will be 9.3 squared, and minimum is 5.4. Let us look at 9.3 squared, 5.4 squared. It is 2.96. It is not more than 4. So it is all right to use that homogeneous variance assumption in this case. But there may be scenarios where this assumption is violated. One other thing is that you really don't get to see the sigma 1 squared, sigma 2 squared, sigma 3 squared, sigma 4 squared, right? In your data, what you have is these guys, 8.5, 9.3. These are not the sigma 1 squared, sigma 2 squared, sigma 3 squared. These are sample variances. They are just an estimate of the underlying truth. So you are making some type of inference about the underlying variances based on these estimated sample variances. So the question is, how do you deal with unequal variances? If you have unequal variances, then our model will be yi1, yi2, yin given theta I, and this time we allow sigma I square are coming from IID normal with mean theta I variance sigma I square. And previously we assumed prior distribution on theta 1, theta 2, theta m. We are still doing that, but now we have sigma 1 square, sigma 2 square, sigma m square. We assume that they are coming from this inverse gamma distribution with parameter this nu 0 and sigma 0 square. Okay, now you see we put prior on mu and tau square as before, mu and tau square. And sigma 0 square and nu 0. Okay. Now let us look at, so what is the difference between the equal variance case and unequal variance case? Can you tell me in terms of modeling? So previously, equal variance case, we assumed that sigma square follows inverse gamma, right? Inverse gamma distribution. And this guy, nu 0, gamma, nu 0 and sigma 0 square, they are all known. This time, we are allowing sigma square 1, sigma square 2, sigma square 3, 4. They are coming from inverse gamma distribution, but this guy, nu 0, I did not assume that nu 0 is known. I put a prior distribution on nu 0. Okay, and this is the thing. This is, we do it. Why? Because we want there some type of shrinkage among the sigma 1 square, sigma 2 square, sigma m square. Okay. So look, when I sample theta 1, theta 2, theta m from IID normal, mu, and sigma square, I did not specify a numeric value for mu, rather I put a prior distribution for mu. If I put a numeric value of mu, then what happens? Then there will not be any shrinkage among those theta 1. So my point is theta 1, theta 2, theta m will not share information if I give a fixed mean value for the normal distribution. But if I allow the mean to be coming from another distribution, then there will be some sharing of information across the groups. And that I wanted. Some information share. Same idea holds for sigma 1, sigma 2 square, sigma m square. I want some sharing of information. Therefore, I allow nu 0 to come from another distribution. Now, you may argue that, yeah, so we are doing that. Nu 0 is coming from this, and sigma 0 square coming from this gamma distribution. Now, what should be the appropriate prior distribution for nu 0? There is no, there is no conjugate type of prior. You can put some reasonable prior. It must be a positive value random variable. So you put some distribution. So Peter Hoff, he proposes a geometric distribution restricted to the positive integer values for nu 0. Now, joint posterior in the unequal variance case, we have many more parameters, theta 1, theta 2, theta m, sigma 1 squared, sigma 2 squared, sigma m squared, mu tau squared, and nu 0, sigma 0 squared. So you have the data likelihood times the prior distribution. As you see, lastly, this is the prior on nu 0, this is the prior on sigma 0 squared. Let us look at the full conditional distributions of the parameters. What is your goal? Your goal is to make posterior inference of the parameter, right? And how do you do that? There is no closed form solution. So you will be sampling from the joint posterior distribution of the parameters through Gibbs sampling technique. Gibbs sampling technique means you will be sampling one parameter at a time from its full conditional distribution. So life was very easy previously. Let us look at the full conditional distribution of sigma I square. It is inverse gamma, good news. For theta I, normal distribution. For sigma 0 square, it is a gamma distribution because sigma 0 square, we put a gamma distribution there. So if you put a gamma prior on sigma 0 square, then you have a gamma distribution for sigma 0 square. But for this guy, this nu 0, it is not coming in a very simple form. It is coming in this form with the prior distribution. You see, this nu sub 0 appears right here in the gamma function. It complicates the entire thing. Also, it appears as sigma I to the power nu 0 as a power. And how do you handle that? So there is no straightforward way of sampling that type of thing. One can use some type of metropolis strings algorithm where you sample from a suitable proposal distribution and then decide whether that proposed value is appropriate for this distribution. If it is appropriate, then you accept that value. Otherwise, you move to the next iteration. This is the idea. Now, it depends on how much effort you want to put here. If you want to write your own code, that is most welcome. That gives you a lot of confidence so that you can solve much more bigger problem on your own. But for these type of problems, you can try some existing software they allow you to specify the log of the posterior distribution, and then they will do the sampling for you. We all want to get some free help, right? So if someone does the sampling for us, that would be so wonderful. So it does, but you have to be careful that the technique they are using, there are several options you can specify. And sometimes you have a good result, sometimes you have a very bad results.